All right, so hopefully the recording will be a little bit better this time. I'm going to use the in-room mics with this setup, so it may pick up a little bit of noise there. I'll just try a bunch of different things in this room as we go through the semester, just to see what's got the best performance here. So there was kind of ugly audio from the first one we could do to those weird technical issues we were having. I think those have been resolved. So we'll see how well this sounds. If this doesn't work, then I'll switch to one of my other contingencies for this room. Real brief announcements. So there is a Muddiest Point due this weekend. A reminder that that's just this little canvas exercise. You could, it could be 5 words, you know, it's asked you 3 questions. The last question, the answer could be NA. It's just what was all the things that we talked about this week. What was the clearest? That made the most sense to you? That's the first question. What was the least clear? So even if everything was clear, what if you were to rank them, what was the least clear, the muddiest? Then that's the second question. And then the third question, is there anything we talked about this week that you thought was particularly interesting, you'd like to hear more about? If there's nothing there, just NA is fine. So all 3 of those are required. Spit those and you'll get your 3 points. So that's due this weekend. I think it's due Sunday. The first concept check will be due next weekend, so that'll be over this unit here. This unit has a couple of core concepts in it, so I've actually got 2 concept checks for this unit. Normally we'll only have 1, so there's another concept check that we do in early February, and then there's the mini project. And so for this unit, the mini project is not droppable, so it's sort of required, whereas the other ones, it's an opportunity to choose which one you want to do. So there are some core concepts in this unit that I want everybody to have at least some basic experience playing with in building your own genetic algorithm. And so that's what that first mini project is. And that'll also be due early February. So the dates are on Canvas. They're a little tentative. If we go a little slower than I had planned through the lecture schedule, I can push those out. Otherwise, they're about where I'm targeting right now. Okay, any questions about the class stuff, about what's expected? Remember, there's drops, these muddiest points. You don't get all of them. I forget how many, but there's several drops for these. Concept checks, there's several drops for those. And again, the mini projects, there's drops, quite a few drops, except this was the one that can't be dropped. Okay. All right, so last time we talked, we opened up the idea that we're going to be, at least in the first half of this course, talking a lot about optimization and automated ways to do optimization. And so when we talk about really hard optimization problems, we have this concept of the heuristic. So a heuristic is a way of solving a hard problem with a set of rules or with a general principle that tends to do well, but is not guaranteed to be optimal. Heuristics themselves have parameters. So there's different ways that you can apply a heuristic, different parameters for the rules that you come together. So in order to figure out the best heuristic, then we have ways to search through the space of heuristics. Those themselves are heuristics, and that's meta-heuristics. And those meta-heuristics themselves may have parameters, and those parameters may need to be optimized with hyperheuristics. As you go from heuristic to meta-heuristic to hyperheuristic, hopefully you get fewer and fewer parameters to the point where if you apply a hyperheuristic, you might only have 1 parameter as opposed to the many billions of parameters you might have in your heuristic. So you gain something out of that by allowing the automation process to do more of the search, and you sort of give less and less input as you go up that hierarchy. So we're going to mainly be focusing on the meta-heuristics, the optimization of meta-heuristics. So let's, make that background, like what's the problem that we're interested in here? And so I talked about it last time that we were working about, in this problem of engineering design optimization, or just simply design optimization, or EDO. So EDO is this name for mathematically formulating a design problem as an optimal choice of parameters for that problem. So for every design, and we'll give examples of these, you have degrees of freedom. So if I'm building a car, there's some things that I'm stuck with. I probably should have round wheels, but there are certain things about, how far apart should the wheels be? What's the diameter of the wheels? There's all of these different parameters, which are design choices. There are trade-offs. If you make the wheels larger, you might get a faster car, but it might have less torque. And so you're going to have different stakeholders, and they'll have different appreciation of these different trade-offs. And there's just generally going to be lots of different things you could optimize and lots of different ways in which you could adjust the design. So rather than just throwing out, saying, well, here's 100 different degrees of freedom, just come up with a design, then engineering design optimization says, let's use automation to guide you so that it maybe can come up with, maybe it doesn't design the car for you, but it comes up with a small set of designs of cars that then you can choose from. So what does that formulation look like? Well, we always have to ask, what are the variables? What are your degrees of freedom? So in a neural network, your degrees of freedom are the weights of the neural network. In a chemical process, it could be the temperatures at different points along the line. It could be how much water you're using, and so on and so forth. So all of these things that are physically possible, that are just up to an engineer or some other designer to coming up with, that's what we're referring to as the variables. I might call these decision variables or design variables. I might call this the decision space or the design space. So it's a giant space of possible choices for these parameters when you come up with these designs. So, and then you say, well, once you have those, then how do we tell the difference between a good design and a bad design? And that's where you have to define a function which captures your objective. Sometimes we'll just call these an optimization function or optimization objective, or just the objective. And so defining this is an art and a science in itself. As we get further on and talking about multi-objective optimization, we'll get into more interesting cases of this, because right now, the objectives that we're going to talk about are going to be a single function. So it's going to be a scalar function. So it outputs a scalar, but it takes in all of these design variables. So what we're sort of saying is that there you have come up with some way to evaluate the choices of your design. So if somebody says, for this chemical process, if you choose all of these things along the way, we can run a simulation of that chemical process, and it will say that it's this efficient. Or it maybe for this neural network, we're going to set the weights up in this way. We're going to set it up with a classification task, and we're going to say that that neural network has this accuracy score. So that score, that is your optimization objective. And ideally, you'd like to maybe minimize that or maximize that. And as we get into multi-objectives, this gets more interesting, and it doesn't become a scalar. It's not a scalar functional anymore, but so that's coming. So it might seem overly simplistic right now, but that's because we're just starting there. So then once we have that, are there constraints? Is it really the case that every weight of your neural network is accessible? Are there coupled constraints? Is it the case that if you set the temperature at this point of the system, does that constrain you to setting temperatures or setting water flow or something like else in another part of the system? So there might be some other constraints that, even though it looks like you've got this giant space of design parameters, in reality, there is, even though you might have you might think you've got the whole, R3 or something like that, where you could choose anything inside this cube. In reality, there is a small donut hole shape in the middle of this, that those are the only parameters that you actually can use, because anything outside of here, your system doesn't function. Maybe it blows up, maybe it just ceases to run, and so on and so forth. So there's this question of feasibility. So that is kind of the last thing here, is what subset of this decision space is so-called feasible. And figuring out that a design is feasible is a complicated problem in itself, because it might be that these constraints, in order to calculate whether you violated these constraints, might itself be just as hard as calculating, simulating the output of your chemical process. So there's a lot of computational challenges in this optimization function. and in these constraints. We're mainly going to be focusing on the function here, and we're going to be punting a little bit on terms of constraints. We're sort of assuming that we have a way of evaluating those constraints and feasibility. But I'll come back to that. I'll hopefully close with this as saying, like, well, what happens if you come up with a design that isn't feasible? How do you deal with that? All right, so that's the basic background. So now I'm going to throw in some math. Any questions about this context, this general idea? It might become clear once we throw in a little bit of the formalization. Okay. Well, all right, so let's see here. So the basic case is this up here. So in engineering design optimization, we have our optimization objective, and conventionally we minimize it. So minimize some function of our design variables. If you want to maximize, you then, whatever the thing you want to maximize, you just put a negative in front of it and then minimize the negative. So that's typically what we do here. You can get more interesting. So you can get optimization objectives, which themselves are, you can imagine this being a mini-max problem. So, or min-max, where you have some function and it's got for a subset of the parameters that are available, you allow for some additional degree of freedom so that you sort of say, imagine like in interdiction problems and adversarial problems, you might say, I don't know what an enemy is going to do, but here's this is the design space of my enemy. This is the design space of the environment. These are things out of my control that are degrees of freedom. So in a worst case analysis, we could say that, on the hottest day possible, so in worst case analysis here, then I want to minimize the chances of an air conditioning failure. So that sort of hits close to home in the brickyard. We're always dealing with HVAC failures. And so you imagine that there are certain variables which affect the HVAC system, which are out of my control. And then there are variables inside the building which are in my control. So I might actually make my optimization objective, I'm going to maximize the probability of failure, but then I'm going to minimize the maximum probability of failure. So min-max probability of failure, where the outer loop, the min, are all the things I have control of, and the inner loop, the max, are all the things that could possibly go wrong that the environment has control of. So there's a lot of interesting types of programming choices you can do inside this optimization objective. And I'm just kind of all putting that behind the curtains and just saying it's just F. So it's the thing that I want to minimize. And I minimize over this feasible set. So this kind of script X that I've got here. So such that, I only want to consider designs that are feasible. So this feasible set X, this could be discrete, continuous, or both. So what I mean by that is it could just be that I've got a set of 100 options and I just want to go over those 100 options. And for 100 options, that's not a big deal. As long as this isn't too costly to calculate, I just calculate this thing 100 times and then pick and that's set. But it can get pretty ugly. You can have discrete problems where you get an explosion there, or you can have a very costly optimization objective where even if you only have 100 or 1,000 of these, it still might take a week to do that calculation of all of those. So maybe you don't want to calculate all of those. So that's what I mean by discrete, continuous, or both. You can have dimensions of this vector that that vary continuously, like a temperature, that vary discretely, like you can choose whether to put one HVAC per floor, 2 HVACs per floor, or 3 HVACs per floor. So I have an example of a discrete variable there, and so on. So that's the basic structure here. And then what are examples of those? Well, or what are the complications here? Well, it might be that your function is costly to compute, so you might have a computation budget. So every design you come up with, every HVAC configuration you come up with, if you need to run that, it might take a certain amount of time. Like I do some work optimizing the placement of, optimizing the operation of reservoirs and the placement of wetlands in very large basins. So like basins the size of Texas. And when we come up with a configuration for that water resource, for those water placement, the simulations that we use to evaluate how well those work take about 10 minutes to run on a relatively decent computer. And so we can scale that up, you know, and you know, we can make that a little bit faster, but we're still talking, you know, several minutes per sim. And there are like 2 to the 900 combinations that I could consider. And so, you know, 2 to the 900 times several minutes means that I cannot look over that entire space just by exploring it in brute force. So it's so those it may seem like a couple of minutes per sim isn't that costly, but it really depends on how big your feasible set is. So that's something you have to consider. The other thing is you may have many local optima. So there might be many choices that you could say, well, for this configuration, if I perturb one of the dimensions of the decision variable a little bit, it gets worse. But if I perturb it a lot, it gets better. So I might be sitting in, so if I have my optimization function over here, I might be, if this is one of the variables in my decision vector, and this is my optimization objective, you know, I might have a situation like this one where there's many of these different optima. And so computationally, if you ask a computer to find the best solution, which would be probably this one right here, so this choice here, locally, if it just takes it just looks around that area, it looks like that's the best in its neighborhood, and it is, but it could be here. And this is also the best in its neighborhood, but it's worse than this one if we're minimizing. And likewise with this one and this one. So you can have many local optima that you have to deal with. So that is an issue you have. And you can also have similar problems with singularities and saddle points. So a singularity, you might have a point in the space that blows up, goes to infinity or negative infinity. And so if you're just walking along that, like let's say you're minimizing a function and you've got your computer is walking along all of the different possibilities and things are getting lower and lower and lower, and they just keep going into the ground. And so it, you know, it might then get distracted by just trying to make things lower and lower and lower. And that may not be, you know, something that, and it may not ever be able to cross that boundary. It might be that things go to positive infinity, and if it could only get past that singularity, it could find a region of better designs, but it gets kind of stuck in this well. So that could be an issue. And then there's this thing called a saddle point, where if we're talking about multidimensional systems, then you can have a case where if you have 2 variables in your decision vector, if you move along one of those variables, they might get worse, but if you move along another one of those variables, things get better. So you can get something that looks like a saddle. So along one dimension, it's sort of as a downward shaping U, but on another dimension, it's an upward shaping U. So it's difficult for me to draw that, you know, that saddle idea. But if you try to imagine you've got one dimension's out here and another dimension's out here, and if you moved along this dimension, you might be getting something that's U-shaped, but along this other dimension, it's an inverted U shape. Then if you were to connect this, if you were to create, you know, look at this manifold that's created there, it's sort of it's an ugly 3D there. So try to imagine that this dimension, this is going along this dimension, and this is going along this dimension. Then you get what looks like a saddle. And that can be complex as well, because you see improvements in one dimension, but you don't see them in another. And that can also trick the tool that's looking for these things. And so, you know, I have to deal with that. And then there's just in general, you find your decision vector is lots and lots of variables. And so we're considering that it's a vector, you know, this is it's in the reals to the n, where n is extremely large. So it's a big space to look for, let alone to calculate feasibility. So with all of that, it's impossible to do a brute force search and be comfortable with the results and then just maximize or minimize over that. So that's the complication. That's what we're trying to solve. And we're trying to use automated ways. We're trying to use intelligent methods that are automated through the use of a computational tool to make this easier for us. Because as a human, if this is the design problem we face, then we just can't do this on pen and paper. Because a lot of times these optimization objectives are something that we can't even write down. So examples of optimization objectives, F. So F can be a high fidelity simulation of a physical system, the wetland system that I talked about. It could be a simulation of the chemical plant. It could be a simulation of a multi-jointed robot as it walks around. And so these are things that it may be impossible to write down a mathematical expression for. And so they reside within the optimization space of so-called SimOpt, simulation optimization. So it's this idea that I have a function I want to optimize, I can't write it down, so the only way I can optimize it is by generating sims of how it works, and then trying a bunch of different configurations, simulating for each configuration. That's so-called SimOpt. But it doesn't have to be a sim. It could be a mathematical expression with no closed form. So there are, it's basically a mathematical expression that is going to be like, F is equal to, and then something where under these conditions, it's this expression, under these conditions, it's this expression, under these conditions, it's this expression. It could be something like the shortest path through a network, and as you change links in the network, then the shortest path can have a qualitatively different shift. If you suddenly open up a shortcut, then you get something that you had the shortest path, it was set, you open up a shortcut, suddenly it snaps and it becomes a completely different value. So you can have these non-closed form mathematical expressions that even though you can write it down, there's nothing you learned in calculus that'll allow you to optimize that thing. You can have loss functions for neural networks. These can be very ugly, lots and lots of local optima, so interesting shapes, and it's very difficult to write them down. You have to sort of explore them using sampling methods in order to figure out the shapes of these loss functions often. And so in this case, your decision vector is the weights of the loss function, or the weights of the neural network. But we could also make F a neural network itself. So one of the things we might do, and then we do this a lot, and I guess I should have written this down as surrogate optimization. So I'll put a different color. So surrogate optimization. And I'll put this as an example of that. So that's not this guy, but this guy. So if you have a really complicated physical system, if it maybe takes you an hour to run a simulation, then what you might do is gather information from the simulation and over time train a neural network to mimic the simulator. And then the neural network is very fast to execute. And it could be we'll talk about the types of neural networks you can use for these that are relatively small and simple to train neural networks, so they don't need that much data, and they become so-called surrogates. And so you can have a simulation optimization that starts out gathering data from a complex sim, but then over time generates training data for a neural network, and then later in the optimization process, it's always calling the neural network. And then periodically it'll check to make sure that if it has a really good solution from the neural network, that it still matches up to the sim. So it'll kind of check in with the mothership back here, and then periodically, if it's still matching, then it'll keep doing the optimization down here. So in this case, the decision space are the actual inputs to the network and not the weights of the network. So that's another option there. Or we can have that it's just it's just the physical system itself. So I have colleagues that have robots that they have a computer tell the robot how to mix a chemical reaction. So let's say they're doing automated drug discovery or automated, just discovery of different chemicals or materials And there are a bunch of different things that they can mix into different physical reactors. So rather than trying to build a computational model of all those chemical reactions, they actually have kind of like a 3D printer for chemistry that will go in, do a little reaction, observe features of that reaction, see if it has the properties they're looking for, feed that back into the computer, and then clean the whole reaction and set the process all up again, and then do that. So then overnight, you can have this thing just sitting at an automated lab bench, creating, trying new chemical mixtures in order to get particular properties out. So you can actually have a physical system is the optimization objective. So you can't write it down, you can't even model it in a computer, you actually just have to go to the real physical system. But if you have a high throughput robotic system to interact with it, then you can do that. Some people use, there used to be a faculty member here who designed multi-robot systems for space. And so over in ISTB4, in Earth and Space Exploration, they had a clean room down on the first floor, a big glass wall, you could watch these things, that had a bunch of sanitized sand that mimicked like a Martian landscape. And he had a bunch of robots that would excavate in this room. And he would run evolutionary robotics experiments in this room where he would say, we would like to minimize the time it takes to excavate this particular area with 5 robots that all can help with this excavation. What's the optimal way to get this team to work together? And he would then try different strategies. He would download them automatically into into these robots, let them work together as a team, see how long it took them to excavate, and then once they got saw how long it was till it reached their goal, then they had another system that could set the whole system back up again. So sort of reshape things up so the sandbox would flatten again, and then try it over and over and over again. And interestingly enough, in that particular case, a lot of times what they found is that the optimal solution for that excavation was for 4 robots to find the nearest wall and just stay there. And the 5th would do all the work, because otherwise they just get in each other's way. So that was kind of an interesting thing, but he learned that from that process. And so, you can actually have these automated systems where the physical system is a autonomous robotic system itself, where you're trying to set the parameters up and you don't trust your robotic simulators, so you just let the robots work in a sort of a physical model. So in that case, it's interesting because they were designing for Mars, but they can't be on Mars. They couldn't model Mars computationally, so they modeled Mars physically in a physical sandbox with these big excavating robots. And so that was something they could do there. So these are all examples, and there's lots more you could come up with. Any questions about this general framework? Yeah.
Could you explain the singularities once again? Sorry.
Yeah, so you can have, so all I'm saying there is, let's add another, is that, so like singularities, saddle points. And all I'm just saying is, you can have an optimization objective, f of x is equal to, 1 over x minus 5. And then, so, what happens at x equals 5? That's the simplest example of a singularity. And, so this function ends up having, it would be something like, so I guess if I'm less than 5, so if I'm greater than 5, it should be positive. So I guess it would look something like this. And so, if depending on how your optimizer works, if it's just sort of, if it trying to find the lowest value, and you wait until it converges, like you wait until it kind of settles down on like a hill, the top of the hill, there's no top of this or no bottom of this hill here. And so you might find that it's just going to keep drilling down deeper and deeper and deeper. And in reality, you're not actually changing the decision variable that much. So it can get kind of stuck digging in this giant hole because it can get better and better. But in reality, it's going from 4.99 to 4.999 to 4.999. So this is just one of the problems that a singularity could cause you. There's all sorts of other numerical issues. I mean, like just the fact that this function behaves so differently across this point. Like it's way negative here, but way positive here. So if you were on this side and you were crawling toward 5, you would be crawling up this. You'd say, wow, I do not want to be anywhere less than 5, because as I'm getting closer and closer to 5, my optimization objective is going in the wrong direction. So if you're just a blind optimizer, you might decide that the solution must live over here. When in reality, you should do some exploration, some random searches, and find yourself on this side. And you find, oh, actually I can get a lot lower if I go there. So that's an example of how a singularity in an optimization objective can confuse an automated search. And it's similar with the saddle points, which I'm going to probably not, I just Google saddle point, you'll get like 3D images that look like a saddle. It's like a horse, it's, riding the back of a horse. You've got, you drape downwards to the horse, but then on top of the, along the backbone of the horse, it goes up, along the horse, it goes down. And so if you have 2 dimensions there, x1 and x2. So on x1, it's going up, and x2, it's going down. And so depending on how you're doing your search, then you might be convinced that you found a minimum, but if you haven't perturbed the other dimension enough, then you haven't realized, well, there's actually things you can get even lower in the other dimension. So there's these complicated structures in these kind of ill-behaved optimization objectives that can confuse kind of a naive optimizer. Any other questions? Yeah.
In the physical system, what would the X be? Would it be like telemetry or input?
Yeah, so that's a great question. So what are these X's? So so this is just degrees. It's a degree of freedom. And so for a physical system, does anybody here have examples? So it's kind of like an improv thing. Can you give an example of a physical system you might ask that question about?
I was thinking the Mars one, but
Like the Mars one, so let's say like for Mars robotic excavation of regolith or whatever they call it. Does anybody have a guess of like what are some degrees of freedom you might have if you're designing these robots? Yeah,
Like energy expenditure?
yeah. So can you be more? Can you think more like? I think this is great. I like the thread. Let's talk about it a little bit more. Can you come up with a more specific example?
Like amp hours of the robotics used, or like travel distance.
Yeah, like how about like
amount of power?
let's say they have to go back to a solar area that's gathering energy. So you're out there searching for things to dig on Mars, and so you have to decide when to come home to charge, and that is a design parameter. So that might be like, do I come home at 20% of my battery? Do I come home at 40% of my battery? And so on. How do we know what's the right choice? If you come home at 90% of your battery, you're not going to get any work done. You come home at 10% of the battery, and there's a significant probability you're not going to make it home. So that's an example where we might want to tweak that parameter and try a bunch of different complex, let's say we're going to make like, we're going to go hills, and like it might be that the robot went out this way where it's flat, but now the straight line home is over a hill. And it doesn't know that because it didn't travel there. But now in order to go over that hill, it has to use up a lot more energy. So we could try a bunch of different return strategies based on battery life. And we might find that when you set it to 20% or lower, then the probability of getting lost is higher than 50% or something like that. So that might be one example. When you have multi-robots, then now you have this thing of like, if I see let's say I see an interesting rock, whatever, so I've got some classifier that says that's probably interesting. Do I decide to go and check out that rock? Because I can also see there's other robots around. So under what social context do I choose to actually go and investigate that rock? So under what density of robots? So if I see an interesting rock and the density of teammates is less than a particular amount, I should go and task myself to that rock. If I'm out of communication distance. But maybe when the density is high, the visual density is high, then I assume they see the rock too, and I go looking elsewhere. That would be another parameter, and so on and so forth. Does that help answer the question? Any other questions? Great, okay. So we formulated our design problem. So what do we use to solve this problem? Now, if this was a basic mathematical optimization problem, like you might be given in calculus class in high school, secondary school, or whatever you call it, if you're asked to optimize a function, what do you typically use at that stage in your career? What do you look for? What was that? Derivative, the gradient. That would be great. If you had a nice function that was well behaved, that you could write down on paper, if somebody says maximize this thing, you say, okay, I'll take the partial derivative of that with respect to the variables that you care about maximizing, and then if I can solve it on paper, I will. But if I can't solve it, if I can at least calculate the gradient, so that's the direction of kind of greatest slope. If I can say at any particular point, so at this particular set of decision choices, so I have all my decision variables, this configuration, then I know that the optimization objective is steepest in that direction. So I might want to walk in the opposite direction. Because if I walk in that direction, I'm going to increase in cost. But so maybe if I walk in the other direction, that's my greatest chance of decreasing in cost. And so those are based on, this was basically inspired by so-called Newton's method. So Newton's method provides a way to solve these problems numerically. If you have gradient, if you have derivative information, then you can use these stepwise methods to try to minimize these functions. And that's, elaborations of things like Newton's method are what gave us things like gradient descent today, or stochastic gradient descent, which is used to optimize a lot of neural networks. And that's great if you have gradient information. But a bunch of those F functions that I talked about, there's no gradient defined for them. What is the gradient of a simulation? You find that a lot of people trying to use neural networks in new application spaces are looking for so-called differentiable models that they can use. So someone may have come up with a simulation model of a chemical system, but they can't use all of the tools to train a neural network are based on having so-called differentiable cost functions. Well, if your cost function involves a simulation model where there's no derivative defined, then you can't use all of those tools. And so now people are saying, can I rebuild a simulator so that it's differentiable? And that way I can then plug it into all of these tools. But that's not always possible. So it can't always get a gradient. There are things that are close to gradient. So there's a so-called, this is a little bit outside of the scope of the things I care about for this class, but I'm just mentioning it. There's something called a subgradient. So there's a bunch of functions that don't have derivatives because they're like, they might have these like points where they look smooth and then they change significance. So like there might be derivatives that aren't defined here because the slope changes on the two sides of this point. And so it's not differentiable everywhere, but you can define these things called subgradients, which are kind of generalized gradients, generalized derivatives that are defined everywhere for these functions. And then there are numerical methods that will use subgradients instead. So there are these numerical methods for what I would still say are relatively well-defined functions. But there's a ton of examples where we can't define a gradient, we can't define a subgradient, so what do we do? And that's the realm of the types of methods we're going to be talking about now in this unit, so-called direct search methods. So these are methods, we use this term direct search, because these are methods that explore F without curvature information. They don't have gradients, they don't have second derivatives, Hessians, they don't have anything that helps them tell me, am I uphill or downhill right now? The only way you really can tell if you're uphill or downhill is by moving to another point and then see, did you go up or down as you move to that point? And so that's what we mean by direct search. And so there are, one of the oldest direct search methods is so-called tabu search, TS. And this is an example of a local search. What does tabu search do? Well, it starts at a guess for a design. So this is a particular battery level that you turn back and go home to charge, a particular density where you help out with the rock, and so on and so forth. All of these things, that decision, you start at some random one there, evaluate how good it is, and then you move to a nearby perturbation of that. So you say, okay, I'm going to add a little bit of random noise to my current decision variables. And so if I'm sitting here, so maybe this is my battery level that I return home at. So that's X1. Maybe this X2 is the density that I go and help others, that I see working on a problem. So I've got those. I'm going to perturb that a little bit. I'm going to step a little bit this way in this axis, a little bit this way in this axis, and then I'm going to evaluate this solution right here. That's referred to as a local search, where you start, it's a trajectory-based method where you start at one point and then you move to a nearby point and see how well things are doing there. And so in taboo search, it keeps track of a so-called taboo list of moves or of locations to avoid. And that taboo list can be built up in a number of ways, but the simplest way is just to avoid previously visited candidates. So you just don't want to do a random search. You like to do a search where you're biased towards candidates that you haven't evaluated yet. So if it's a discrete space, so there's a countable set of options on this axis, a countable set of options on this axis, then it might be that there's a countably infinite. So there's an infinite set of options, but I can keep track of the options that I've tried before. So I've tried this one before, so it goes on the taboo list. So I try this one, it goes on the taboo list. Now, because that one was on the taboo list, I'm not going to step back to there. So instead, I'll choose another point. Maybe I'll choose this one over here. Now, all three of those points are on the taboo list. So it's a really simple idea. I just randomly move around a space, keeping track of where I've been and avoid going back to places that I've been before. That's the basic taboo search. There are other type versions of taboo search that have more complex taboo lists, but this isn't really a class about taboo search. I just want to set it up as like a basic benchmark here. Now, if you're walking around all these, then you're also keeping track of the best you've seen so far. So the taboo list might include your optimizer, but it's just saying don't go and reevaluate that because you don't have to pay that cost again because we've already checked that one out. So that is a simplest version of a direct search method. So we want to try to do better than for a while, like in the 80s or whatever, taboo search did pretty well. There are versions of taboo search you can still find implemented, but we'd like to do something a little more intelligent than taboo search. All right, so that's what we're setting up here. So we're going to start introducing algorithmic approaches that bring us close to the genetic algorithm, which was the subject of this unit. All right, questions about what I mean here about how the taboo search works? Start at a random point, and then you try new points, and you don't go back to old points. Okay. All right, so there are nature-inspired examples of these direct search methods. The GA, which we'll talk about in this unit, ant colony optimization, which we're going to be talking about in a later unit. So I'm just bringing those up, that those do fall into direct search. In all direct search, regardless of their nature inspired or not, there's basically two categories. The first category are like taboo search. These are trajectory-based methods, local search-based meta-heuristics. So taboo search is an example. We're going to learn about simulated annealing in a couple of units. That's another popular one where it starts in one place and then it uses a certain logic to move to another place. And so that is an example of another trajectory method. So there's just one of them moving around and it's moving from one spot to a spot, usually relative to the old spot. The other more example, which genetic algorithms fall into, are population-based methods. So GAs fall into this and all other so-called evolutionary algorithms. So I'm going to define what these are here in a second, but I'll just go through and list a couple of these. Ant colony optimization, particle swarm, we'll cover those much later in class. There's a bunch of more like harmony search, which we don't talk about in class, but that's one that you could cover in a project at the end of class, for example, and many more. All of these population-based methods, as I'm going to show you, they put out multiple searchers. that move around simultaneously. And usually it's not like running tabu search in parallel. Usually they communicate in some way. So they are coupled together. So if you just did like tabu search, 100 parallel tabu searches all starting in a different spot, it would go 100 times as fast, but there wouldn't necessarily be shared memory between them, so you might get redundancy. It might be that one searcher starts searching spots that the other searchers have already seen. So what these do is they put out a population of optimizers and try to use that population to help inform the next steps of every member in that population. So that's what this family does here. And you can further divide up these things based on whether they use memory, just like tabu search is like a random search with memory. So there are other categorizations some people further break this down into, but I'm just mainly interested in trajectory methods. So for this class, it'll be like simulated annealing and population-based methods. So for this class, it'll be like the GA and other evolutionary algorithms. So those are the categories we're setting up. So let's see what I mean by these direct searches and then what I mean by an evolutionary algorithm. So this is the basic flow chart for any direct search. You start with an initial guess of what you think might be a good design, and then you run your optimization objective. You run that function, you run that simulation, you run that real system, and you see how well it did. And it may have done really poorly. You may not know whether it's poor or not, and it'll sort of establish a baseline for the rest. And then after you evaluate that function, then you take some output metric of performance and you run that into your optimization algorithm. So this is what changes from optimization algorithm, from direct search method to direct search method. It's what goes in this box, the method that does this. So there's some algorithm which chooses the next point or set of points. So if it's a trajectory-based method, it'll be a point. If it's a population-based method, it'll be a population. So you might start with a bunch of function evaluations. That set of metrics goes out, goes into here, and then it comes up with a bunch of other ones to try in the future. That's how a population-based method would work here. So then after you calculate those new ones based on the performance of the old ones, then there's going to be some termination condition. And sometimes you can swap the order of where this termination condition comes into. I'm just putting it here just for simplicity. And what do I mean by a termination condition? This will be, say, based on convergence or your computation budget. So you can say, like, I've tried 100, the last 100 iterations. So the last 100 solutions I've tried, the optimization objective hasn't changed by more than 2% or something like that. You could come up with some criteria, and that would say things seem pretty flat here. I might be able to get a little better, but it's not worth the time. I'm going to stop here. Or you might just say, I'm only going to run 100 loops, 100 iterations through this thing. So that could be another way you do this. So you come up with some stopping condition. Remember that we don't know, we will never know what the true optimizer is. So it would be great if we had an oracle that said, aha, you found it, that's the true optimizer. Then we could just run this thing until that oracle tells us that we're done. But we're never going to know that we hit the true optimizer, and we may never find the true optimizer. So there's a speed accuracy trade-off here where we can let this thing run and run and run and get better and better, but eventually we have to throw up our hands and say that's good enough. And that's what you encode in your termination condition. So if you decided that's not good enough, then you're going to go back to your function that you're going to evaluate and evaluate your new population or your new set. You could do memoization here. So this term memoization, kind of from the systems community and the database and also so this is an idea that you can keep track of if you've ever seen that input before, then you don't run the function. So if it takes 10 minutes to run the function, but you might have had the bad enough luck that you chose, this is a little like tabu search, avoiding things that's done before. If you happen to choose a next solution that you've already run through this thing, then you just look it up in a lookup table to see what the value is for that, and then you can skip the costly evaluation for that one. So that's an optimization you can do here too, memoization. And then alternatively, if you did converge, then you give you results. And so for a trajectory-based method, it'll be in points. You'll say, this is the best that I have found. For the population-based methods, you could look over the population and say, of the 100 optimizers I've had running around in parallel, this is the best optimizer. Here's your result. But a lot of times that throws away really interesting information. So sometimes in a population-based optimizer, we actually tell the stakeholder, here's the best one, but by the way, here's a bunch of others that were kind of in the mix. And then, because sometimes someone will look at those others and say, oh, that's interesting. It's true that this one technically is the best, but there's this optimizer over here where you don't drop the optimization objective that much, but it loosens some other issue, reduces some other issue that wasn't captured in the optimization objective. It might be cheaper. Let's say my optimization objective was all about energy use, and I didn't actually put dollars into my optimization objective. But if I output a bunch of solutions out here, and this one happens to be the one that uses the least amount of energy, but this one maybe uses a similar amount of energy, but is $1,000 cheaper, then maybe this one, even though it's not quite the most energy efficient, it's so much cheaper that it's worth it. And so sometimes if you are using a population-based method, you output the population just because there can be valuable information for your stakeholders there. So that's the basic outline, just this kind of simple loop there. Any questions about what I mean? Any direct search algorithm is going to look like this. And what's interesting comes into what you put in this box. So that's the stuff that we focus on. So questions about this overall structure? We're not going to spend very much time at all on how to set these termination conditions. I know sometimes questions come up about that.
Yeah, will we spend time on learning how to implement this in terms of like a particular system that we choose?
Yeah, I mean, so like mini project one, you'll be asked to implement from scratch a genetic algorithm in a very basic level. So it'll be, giving you an optimization function which you actually could optimize by hand, but then you'll be implementing it for that. And then if you had a system, like a simulation of a real system, for example, then the code that you used that evaluated, the point where you evaluate that simple function, you could imagine getting rid of that and say, okay, I'm going to make some API call to my physical simulator or whatever, and then get data back from that. And then otherwise the algorithm would be the same. And in some of the resources that I've shared online, there are pseudocode in the Canvas module for this, for a bunch of these direct search. You can kind of see how other people have implemented them. And I don't care when in the solutions to these mini projects and so on, I don't care if you're using Python, MATLAB, or Java. It just has to be results that can be parsed by the grader. And so there has to be, it's more of an emphasis on clarity. And again, I won't be looking for unit test results. So it won't be like I'm expecting a particular answer. It's more I'm going to ask you to explore it and then tell me something interesting about the algorithm and use a quantitative result that comes out in order to justify that thing that you're telling me. Does that answer your question? Okay. Yep.
Where does A-star search or beam search fit?
So if you have, there's questions that there are sort of these planning methods from AI that involve that you can use to search through spaces in this as well. And so those methods themselves can be put into this kind of search taxonomy, where the ways in which they come up with, like if you've got, these are methods like if you've got a Waymo vehicle, and or a Tesla or whatever, an autonomous mode, and it can plan certain trajectories that it can drive ahead of it. Then there are these, these RRT star, all these other different search methods that can say, well, there's all these feasible ways. I can drive straight, I can drive in a curve, and all these things, so I can look across all these different things, and then based on all of these geometrically feasible options, then I'm going to pick one that actually fits my route the best. And then I'll drive that. And so you can think of a lot of those methods and as a lot of them are like population-based direct search methods, where they're coming up with a set of options. They're evaluating each of those options based on some metric, and then they're coming up using some clever method to come up with a new set of options. So those definitely can fit into this taxonomy. We're not going to be talking about using A-star, RT, et cetera, we're going to talk more generally about these problems that don't necessarily fit those, but it's interesting to sort of think about, for a problem that I would solve with a genetic algorithm, could I use these planning methods to solve this particular problem? And I think those of you who are familiar with reinforcement learning, there will be other similar things there as well. Like you can imagine this optimizer that's moving around in this direct search, maybe that's a little robot, running a little reinforcement learning algorithm. It gets a little bit of a reward for how well it did here. So then it goes and it moves to this other spot in the configuration space and it sees, and so you can imagine that it might learn the shape of the optimization objective as it moves around. So a lot of the direct search methods are going to feel like some of these reinforcement learning approaches. And there's definitely overlap there. Some of that is intentional. Some of that is just different communities coming together after being decades apart in the kind of intellectual space. Any other questions about direct search? All right, so let's drill down then and think about, this unit's going to be focused on the GA, which is a type of EA. And an EA, an evolutionary algorithm, is a type of population-based direct search. And so that's what I'm just emphasizing here. So an EA chooses a population of possible solutions at each iteration, and we're going to call those iterations generations. And then reshapes the population based on relative success. So this is what differentiates it from other population-based methods. So when we look at ant colony optimization later in the class, when we look at particle swarm optimization later in the class, they also maintain populations of optimizers, but those optimizers aren't competing with each other. They are working together in a more collaborative way. This is a much more competitive way, where each optimizer, it's going to have, I'll just define it here, it's going to have a fitness. And that fitness will be the number of individuals in the next generation, the next iteration, based on an individual in this generation. So if I have if I say this individual sitting right here in configuration space, in the decision space, if it had a really good optimization value, it might, then in the next generation, it might generate a bunch of offspring which are peppered around its location in the decision space. So one of its offspring is right here, the other offspring is right here. So there's a cluster of new individuals in the next generation. Now, each generation can only have 100 individuals. And so one of the 100 from this, generated 50 individuals. This one over here is in a really bad spot in the decision space. And so it only generates one offspring. So we've got 50 offspring were generated from that one. One were generated from this one. So overall, we might see an expansion of the population from 100 to 500. Well, before we can run the next iteration, we got to then cut that back down to 100. Well, the one who produced lots of offspring is more likely to keep offspring in the next generation when things are arbitrarily cut back down. Whereas the one that only produced one offspring is more likely to be left out. And that's the key idea behind these evolutionary algorithms, the survival of the fittest. Fitness is formally defined by the number, so it's basically for every solution, you look at the number of representatives of that spot in the decision space now, and you look at the number of representatives at that spot in the decision space or around that spot in the next generation. And if you divide that together, that's the fitness of that spot. So fitness, like a loss function, is defined across the decisions, across the configuration space, the decision space, these design variables. And so you can imagine every point has a fitness, and you can think of that as if you were to calculate the optimization objective here, how many offspring would you produce? And so part of the challenge of the evolutionary algorithm will be to implement this fitness function based on the optimization objective. And that will be what that will cause things. That will mean that if you happen to be here, you're going to produce lots of offspring. If you happen to be here, you produce few offspring. And based on how we map the optimization function to the fitness function, we will get, we can amplify, like if there could be small changes. So our optimization objective might have these little dips in it. And that optimization objective might have these little dips here, but if we choose a mapping of our optimization objective to a fitness function, which has a really strong pressure for doing better, then those little dips may turn into giant hills of the fitness function, where we want to maximize fitness even though we're minimizing the objective. And that might mean that you might have started out with individuals all over this space, but now this little difference that makes this one a little bit better than all the others is going to mean the next generation, you're going to have, I meant to try to draw the same shape, but in the next generation, something like this, then you might have all of your individuals here, because there was that huge sensitivity to small changes in the optimization objective. So that's part of the art of designing evolutionary algorithms, is the mapping from your objective to your fitness function. And that tunes what we call, and we're going to get this into this more detail next time, selective pressure. So selective pressure is basically this number and how it relates to the optimization objective. So different points in space are going to produce different numbers of offspring, because you have to call those offspring down to a finite number to go through the algorithm. Then if you can produce more offspring, there's more likely that you'll stay in the next generation. And that is so-called survival of the fittest. So those strategies to produce more copies will be more likely to stay in the population and even crowd out other strategies or solution candidates. And there are lots of evolutionary algorithms, not all of them are the genetic algorithm. So the genetic algorithm, which will be the key focus of these first couple lectures, is a particular way of doing this. But there are lots of evolutionary algorithms that take this approach. So the genetic algorithm is a particular way to create those new offspring. So a genetic algorithm creates a set of genes. So it defines the decision variable, this vector, decision vector, as a chromosome that is perturbed in gene-like ways. And that's how it produces new offspring that way. You can produce new offspring lots of ways and still have survival of the fittest apply. So anything where the survival of the fittest applies is an evolutionary algorithm. A genetic algorithm, it's not only has survival of the fittest, but the way in which you produce new offspring is going to be very gene-inspired. All right, questions of what I mean by an EA? And then this will become clear as we start talking about the genetic algorithm in population genetics. This will become clear because the GA is a great example of an EA. And so we'll start seeing this more and more as we get the implementations of there.
Yeah, I imagine that the evolutionary algorithm has been around for a long time. What are some of the modern implementations?
Well, so we're going to, so there's the, like you can find the GAs implemented. There's a, there are genetic algorithms that are already implemented in a bunch of Python libraries, in MATLAB, and any good numerical tool is going to have optimization meta heuristics and will have like a GA that's implemented. And so we're going to talk about the basic GA and the challenges with it. And those modern approaches that if you were to download a modern numerical software package, it will look a lot like the GA that we will be using, but it will have implemented some of these things that address the challenges that I'll bring up. It'll already have that done. And then now, really the big, like with the GA, the interesting thing is there's the multi-objective GA. So it turns out that population-based approaches are really good at multi-objective optimization, which we won't get to until like the like the unit 4 or something like that. So, but in multi-objective approaches, there is still work in developing novel genetic algorithms that are better and better at the multi-objective problem. That's just because the multi-objective problem is so hard computationally. So it's true the GA has been around for a long time. Some people have used it as a toy model to understand evolution, but in this class we're focusing on its tool for design optimization. There are alternatives to GA in learning, like when you have to say for this particular system, is this better for, like, you can, in MATLAB, there is a very good particle swarm optimization built into MATLAB. And there is a very good genetic algorithm built into MATLAB. But for the different types of problems, I might want to use a GA or a PSO. So if I want to optimize a neural network and that neural network uses a loss function that's uglier, it's too ugly for me to use stochastic gradient descent, I might want to turn to one of these methods. But I wouldn't probably use a GA. I would use particle swarm optimization. We'll talk about that why. PSO was developed to optimize neural networks because the GA wasn't very neural network friendly. So these methods, just because they sound cute and they seem like they might work, it turns out certain optimization objectives are better suited for certain optimizers. So there's a no free lunch theorem. There are a bunch of no free lunch theorems, but so there's an NFL, no free lunch theorem of optimization, which basically says there's no perfect optimizer. Any optimizer that shows tremendously much better performance on one optimization objective will be much, much, much worse. There will exist another optimization objective where it is terrible. And so part of the challenge in choosing your meta-heuristic is learning, based on what you know about the problem, what type of meta-heuristic is most likely to work out better. So I think it'll become clearer as we go. Any other questions? Yeah.
You talk about heuristics, but where is the heuristic part?
Yeah, so the EA is a meta-heuristic, and the candidates that it's solving for, the X values, those solution candidates are the heuristics. So they're heuristics in that you can say, like, say I optimize this artificial neural network with a genetic algorithm. And so somebody would say, oh, so is this the best set of weights? I'd say, no, it's not the best, but it's pretty good. So the neural network that comes out of this is the heuristic. So you're saying, why did you use this neural network? Well, I used this neural network because the genetic algorithm tried a bunch of neural networks, and this is the one that beat them all out. And so I used a meta-heuristic to come up with a good enough rule that seems to be working for my cat-dog classifier. Okay. Other questions about that? And then the GA will have its own parameters, and choosing how many individuals are in every generation. What are the mutation rates, all those sorts of things. You might build a hyper-heuristic that tries a bunch of GAs with different population sizes and so on. And then it will then converge on the right GA configuration for your problem and then run the rest of your problem through that configuration. And if you go in and look at how modern GAs are implemented in Python libraries, in MATLAB, you find that they often might include a little bit of adaptive tuning built into them, and that's them effectively encapsulating a hyper-heuristic inside their meta-heuristic in order to say, for this particular problem, we're going to fine-tune this particular way. All right, we're almost done here. So I mentioned I wanted to at least say a couple of things about this. When you're designing these optimization heuristics, you're coming up with all of these solution candidates. That candidate may numerically fit inside, it may look like it's a number, but is that number feasible for your optimization objective? Can it actually be calculated by your optimization objective? Is it a feasible solution? Is it actually a design that can exist in the real world? Does it violate a conservation of matter or a conservation of energy or other conservation laws? So that's an important thing that you have to consider before you iterate through this. And so, and the big question is, if you have decided that it's not feasible, what do? Do you remove it? And there's some arguments that you actually leave it in your system. Because if you can evaluate your optimization objective for the infeasible solution. So it's not a solution you can actually give to your stakeholder. They would fire you if you gave them that. But it might be a solution that, like, if your feasible set was this ugly feasible set, so this is some subset. So you might have these are all of the possible values can fit inside this rectangle. But the feasible ones that you actually can implement are in this funny shaped thing. Well, if you happen to find an infeasible point right here, rather than discarding that, if you leave it in, it might provide you a shortcut to get from this space to this space. So sometimes if you know that it's infeasible and you refuse to that be your solution, so you remember the last feasible solution was over here, it allows you to tunnel out through the infeasible area to find other feasible areas maybe more quickly than if you were to restrict yourself to try to only work within the feasible area. So sometimes you don't want to throw out those. They actually might be helpful to keep in there. So an alternative to exclusion might be just penalizing. So this falls under the subject of soft constraints instead of hard constraints. So what I mean by that is, rather than saying that the optimizer is not allowed to live out here, what we can say is we're going to add a tremendous cost to the optimization objective for every point outside here. And that allows the optimizer to dip its toe into those waters. But it's probably not ever going to select those because they're probably going to be inferior. But if it needs to, it can still move into that area. So that is maybe an attractive way to handle that. So that's so-called soft constraints, where you don't formally define this area as the only allowable area, but you make it a very low cost area by adding cost to the infeasible area. The alternative is to discard it. So if you discard it, then you run into the problem, well, then how do I choose another? So if I was at this point here, then how do I end up choosing a feasible point? And that can be an issue because you can so-called project your current point onto the feasible set. So you can basically ask, of all of the points that are feasible around this point, which one is closest? That's what we mean by projection. That in itself is an optimization problem. So because you have to basically say, I'm optimizing, like I'm infeasible, there's a ring of feasible around me. I now need to calculate the distance to every feasible one and choose the one that's the minimum distance around me and hop to that. So that itself, depending on how things are set here, can be a costly thing to run every iteration. So maybe you don't want to do that. An alternative is you just randomly choose a new one. So I'm in an infeasible area, I'm just going to randomly draw, and that might land here. But it might land over here, and now I'm infeasible again. So now I have to randomly draw again. So if your feasible set is very small, then it might take 100 random draws before you manage to land inside here. So that is going to be costly as well. So discarding these infeasible points and choosing another invites costs. But keeping them may sometimes assist things, but that is assuming that you actually have a simulation, an optimization objective where you can keep them in. So this is a complex topic, and it's sort of outside of the scope of the key focus here, but it is important. So when you design these metaheuristics yourself, you will have to deal with this. And I don't want to make it sound like this is an easy problem. It's just not the problem that we're focusing on in this unit. It's definitely an interesting problem. All right, so next time we're going to then set up for the GA by introducing a little population genetics. So we're going to talk about selection and drift and the pressure between. Any questions? Okay. Thanks for all your questions today, and have a nice weekend. Don't forget about the Buddiest Point. See you next week. Okay. Yeah.